configuring a design improvement study from scratch, and then I'll show you how to monitor or post-process such a study. So the way you start is you kind of work your way across these tabs, doing sort of one action in each tab. So we start by creating a new design improvement study by clicking here. And so basically you can name your study. What is the study based on? It can be either based on the physics simulation, the FEA analysis, or you can actually do studies over just pure geometric manipulation. So I'll do the study over the physics. You can initialize the study from other studies. So I have some other studies I ran before. I can suppose I want to use the same variables again. I can select them there, but for this demo, I'm gonna start from scratch. So you see all the steps in building a study from scratch. So I'll say OK, and now you see as in the tree on the left, we've got a new study that's been created under the scenario, and but it's not ready to run yet. So we're going to next go to the Design Variables tab, and this is where I identify the input parameters that I think are relevant for the study. So in this particular a bottle example, I'm going to operate on a number of different CAD parameters. So I want to vary the CAD geometry of the bottle as part of my study. So I pick those parameters. I've also got some parameters associated with the mesh. So there's a set of parameters here related to how we mesh the thing. So I'm going to pick those parameters as well and add them to my list of design variables. So you see now my study is growing. I have some features under the study, 12 design variables so far. The values were pulled in from KnowledgeWare. If there are KnowledgeWare ranges defined, we pull those ranges in as well. If they're not, then you can set the ranges here. I can at this point preview what does it mean? What do these parameters mean? So like radius ribs top, for example, we can maybe guess what that means by its name, but let's just maybe vary that and preview in this geometry. What does it mean to change the radius ribs top parameter? And so you see what happened is these are the ribs of the bottle, and they got a lot thinner. So one at a time from here, I can preview the effect of changing any of these parameters on the geometry. Okay, so those are my inputs. We'll go to the next tab. This is the response variables tab, and it's here that I'm going to bring up the response variables manager and pick the output parameters of interest. So from this parameters area, I've got a couple of outputs of interest. So there's actually an inertia measure, and so I can get the volume of water and the mass of the water in the bottle. So these are purely CAD outputs. I also have some FEA outputs. So we have some sensors down here in the results. So like a maximum von Mises stress sensor, that's going to be of interest to me in my study. A mass sensor, I can get the mass of the bottle here. So these are the outputs that I want to consider in my study, and I can actually define even objectives and constraints from this response variables manager. So I'm identifying for the study what I care about in terms of performance of this bottle. So for example, maybe I want the water volume to stay at a certain level, so I'll set a target objective on that. Maybe I would really like stresses to be low in my bottle, and I'd like the mass of my bottle to be low. So I could set those as objectives that I want to minimize. And maybe I have some constraints on these, like maximum allowable values on the stress level or on the mass. I just set some maximum. So as I'm filling that out here, I'm again building up my features for the study. So I've done the inputs, the outputs, constraints, and objectives. They've all been defined. So I really like using those managers. We have the ability to create one at a time design variables or response variables or objectives or constraints, but you can kind of do them all at once in those managers. And then we're almost ready to run. We have this design space checks functionality that we've put in this app that allows me to kind of assess the readiness of my model before I actually run it. So what I see here is a 2D cut through this 12-dimensional space, and I'm plotting two of the inputs against each other. And this is just a kind of a picture of what points we might run in an exploration. And from here, I can take any point in this from these set of points, and I can check what does it mean to what does that point look like. So instead of varying one geometric parameter at a time or previewing one geometric parameter at a time, I'm previewing the change to the bottle of all 12, and I get a pass or fail kind of a score here. So what we see with a lot of CAD models is if I do any parametric variation, suddenly the CAD model doesn't regenerate, and so it's not appropriate for design exploration. I need a robust CAD model that the geometry for which regenerates as I vary the points. So I've spot checked a couple of points too. They both succeeded, so that's good to see. I can click this check all points button, and it will cycle through all 120 of these points and check them. That'll take a little while. I could reduce the number of points, say, maybe I want to just spot check 15 points across the space. I could check them all before doing my study. I can see, how much of the space would I cover if I were to do 1,000-point exploration over this space. So this is a graphical view of the design points that are going to be run. We also have a tabular view of what you may be used to seeing in the classical view of a design matrix. They're both available to you. We also have different levels of checks. So I just demoed the model level check, and that's just a CAD preview. But I can also do a model plus mesh check. So basically, I would not only update the CAD, but I would remesh and see if that succeeds as well. And then we have a model plus mesh plus scenario level check. So does it remesh after the CAD change, and are the loads and boundary conditions all still valid after that change? So we can assess what fraction of the points do we expect to be able to succeed using this nice little tool before we actually run the study. Okay, so that's that step, and then the final step is we hit the simulate button, and this is where you configure the type of study you want to run. So you say where you're going to run it. The way I typically run is I'll usually run remotely, and I will configure this to run. What I usually do is I send it all off to remote compute resources, and any station on my server that's available to take on work, it can be done this way. So we typically have maybe 20 or 30 stations connected to our server to choose from, so you can run them on any one machine. But by configuring it like this, now it says that the study's controller will run on any available station, and each individual simulation will run on any available station. And I'm going to do a 120-point exploration. And here's that sequential versus simultaneous input from the user that Christina was going over in terms of the cost of this. So I could run this 120 points sequentially, one at a time on my local machine. I can run them 20 at a time on these remote machines. I can control that, and then with this new cost model, we can trade off speed of the exploration versus the amount of tokens that the user has to pay for to accomplish their exploration. So I'm not actually going to run this one live for you because it's going to take about a half hour to run. So I've ran this one already before the call. So when you hit that run button and you start your study, this is the user interface that pops up, and it's the same exact interface whether you're running the study or whether the study is complete. So we wanted to ensure that so some of these studies may take many hours or even days to run. We want this sort of an interactive environment to see what's happening in the study as the study is running. And so it consists of a scatter plot, kind of an image viewer in the middle, and a parameter table on the right. And you see what happened in that study I ran. I did 120 points, and they're shown here in the scatter plot. So each Each little dot in the scatter plot represents a physics simulation that I executed, and I can preview different, or I can see different views of that. So there's some best design of the 120. There's some Pareto optimal design since we have multiple objectives. There's some blue points that are just feasible, meaning they satisfy the constraints, but they're not the best. There's some red points that mean some constraint is violated, and we see which one as we click on that. There's some failed points, like this is a failed point. So why did it fail? We don't actually have any physics result. We do. If you click over here, we do have a geometry for that. So we can actually go and right-click here and see the diagnostics for that point, and we show the data and message and status files from Abacus. So we can go in and see, oh, it didn't converge. So we know exactly why that point failed. It's a physics simulation convergence issue, and we have a failure over here. The red indicates that the geometry didn't even update. So 2 out of 120 is not so bad in my experience. So the model is pretty robust, but it's not 100% robust. If I click this info over here, I will see what was the performance of my study. So I did 120 points. They all completed. The average simulation time was 3.5 minutes for this model. The overall exploration took 34 minutes and 51 seconds, and the reason it was able to run faster than, say, 360 minutes is because we ran in parallel. So sort of the velocity of the study is at the bottom there. So 3.4 simulations per minute were coming back into this tool as I was running. So maybe you could do a live demo of executing with a model of this complexity if you have those stations available to you. So some other interesting things to look at on the performance side is this. So I plotted time, run ID versus time, but I can also plot run ID versus analysis time. So time is since the start of the exploration, when did this point finish? Analysis time is how long did each individual point take to run. So you see some interesting things about our compute orchestration layer is each of those stations take a little bit longer to run their first simulation than subsequent simulations. So that has to do with loading the entire model onto the station. But then after the first 20, on the first 20 stations, the rest of the runs are much faster. I can plot any input versus any input in that scatter plot, and I can actually control them with this little shortcut here. So I'll plot maybe the radius of the ribs, the two rib radii parameters. I can kind of click around here. So this is a design where all the ribs are small. This is a design where both sets of ribs are big, and the best happens to be there. So I can kind of see maybe some patterns in my data, a lot of infeasible designs down here, some more feasible designs up here. I can plot input versus output. So maybe I'll put max stress on my y-axis so I can see a lot of scatter there. So max stress versus the radius of the ribs at the bottom. I don't see a clear trend, but if you switch to radius ribs top, you do see a bit of more trend there. So that parameter is clearly having a big impact on this stress constraint. I can plot output versus output, like mass versus stress. So again, I'm seeing output versus output in this, and I can click around in here. So these designs have two constraints violated. The good designs are down here. I can select any of the designs, like maybe these are the interesting looking designs, and I can play through those designs in this viewer. So what do the good looking bottles look like? So it's kind of an animation of the good bottles. I can pick some of the bad designs up here. What do those look like? Just play through those similarly. A lot of capability here. I won't be able to show it all in the time we have, but I'll show a few more things. Like I can select all the points, and I can look at them side by side. So this is, and actually I can choose any way to sort these. So what I'll do is I'll sort by rank. So now I'm seeing a side by side list of all 120 designs sorted by rank. You see the worst design. We rank the failed points at the bottom, right? So those are those two worst, and then the best is here at the front. And I can look at the parameters, either the actual values or the diff or the percentage difference. I can look at thumbnail grid of all the designs. This is a kind of a view that I like to use. I would say for this, depending on the model, you know, for this one, the kind of geometric changes I'm making, maybe it's hard to see what's really the difference between that bottle and that bottle. I can click around and see their parameter difference, but so you have both options available to you. You can look at the kind of a grid of all the designs and different resolutions of that, different size of that, or you can use this sort of a view to you know, watch. So I can really see what are the differences as I superimpose those designs on top of each other. And every field output is available at every camera view. So lots of different views of the data to visualize what exactly is going on. Last thing I'll show before, well, a couple more things I want to show. One is filtering. So we have 120 points here, and maybe we'd like to filter that down some, not have to deal with so many points. So I can go to the filters from the left, and I can just immediately get rid of some points. So maybe I'll filter out the failed runs. So I'm down to 118 out of the 120 being active. Maybe I'll even just throw out all the infeasible designs immediately. So that gets me down to 42 of the 120 remaining. I can zoom in on those remaining designs. So now when I play, I'm not considering any of the infeasible or failed runs. I'm just looking at the feasible points. And even we can put filters on individual parameters. So maybe I have this number of points left, but I want to kind of focus in on the ones that have a certain water volume range. So a way to down select and, you know, dig into the data in a kind of an easy, intuitive way. You can declare favorite designs, just like you would bookmark a web page. You can say, well, this is a favorite design of mine, and this is a favorite design of mine for whatever reason you have as a user. And then we can do side-by-side comparison of all selected designs, or we can do side-by-side comparison of all favorite designs. And so the favorites are saved as part of the data model. So when next time you come into this app, it will remember the favorites that you found. And then the last thing you might do from this app is generate alternatives. So this is